Error rate on search result pages jumped from 0.02% to 3.5% within minutes. An unclosed tag with a long attribute caused the parser to allocate an unbounded buffer, corrupting the index segment being written. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover design Google search. Google search decomposes into 4 main layers: a distributed web crawler, an indexing pipeline, a query serving stack, and a ranking system. Each layer must handle failure gracefully and scale horizontally. The inverted index is the heart of search. Instead of scanning all documents, you look up the term in a hash map to get a list of document IDs. In production, this is distributed and segmented. Here's a simplified inverted index lookup. The index map stores term-to-posting list mappings. In production, this is distributed across shards and uses compressed posting lists with skip pointers. The crawler discovers URLs from a seed set and downloads each page's content. At Google scale, you need a crawl budget and politeness to avoid overwhelming servers. This crawler worker fetches URLs from the frontier and uses a per-domain rate limiter to enforce politeness. The acquire call blocks if the domain is being hit too fast. The indexing pipeline processes crawled HTML through parsing, tokenization, stop word removal, stemming, and finally building the inverted index. Segments are immutable and merged periodically. This simplified segment writer builds an inverted index in memory and writes it to disk. In production, you'd use compression and skip lists, but the core idea is the same. When a user types a query, the serving layer parses it, looks up terms in parallel across shards, merges the top results and ranks them, all in under 200 ms. The query parser applies spelling correction and tokenizes the query. Spell correction can add 10-50 ms if not cached, so precompute corrections for frequent queries. Modern search uses multi-stage ranking. First, BM25 retrieves a few hundred candidates. Then, a deep neural network re-ranks them using hundreds of features like click-through rate and page freshness. BM25 scores documents based on term frequency and inverse document frequency. Higher TF means more relevant, but with diminishing returns controlled by K1. Longer documents get a penalty via B. Google uses a 2-tier serving architecture. Leaf nodes hold index shards, and the root aggregates results. Sharding is hash-based for even load, and each shard has at least 3 replicas. This shard router maps a term to a list of replica nodes using consistent hashing. The replication factor ensures fault tolerance. This is the same issue we highlighted at the start. Here's exactly why that happened. A buggy CMS served malformed HTML. The indexer parsed it into a corrupted segment. During merge, the corruption propagated to a new segment, and replicas synced the corrupted data. Queries against those segments failed. The fix was to add checksum validation after every merge. Each segment now includes a checksum field. After merge, the new segment's checksum is verified before it's exposed to queries. If it doesn't match, the merge is rolled back. A team used a feature computed from future click data. Offline validation looked perfect, but online CTR dropped 15%. Always validate that all features are available at inference time. This is the exact mistake that caused the incident. Without checksum validation, a corrupted segment from a merge can spread to replicas silently. Always verify checksums after every merge. Segment alignment to cache lines matters. Misaligned posting lists can leave 30% performance on the table. Always profile your memory access patterns. A misconfigured CMS caused a redirect loop that consumed 40% of a region's crawl budget in under an hour. Always bound redirect depth to 5 hops and set a per-domain redirect limit. A default split on whitespace treats Café and Café as different terms. Always apply locale-specific tokenization and Unicode normalization to avoid missing matches. A bug in the query rewriter turned the query into a 50-term OR expansion, generating 500 million candidates and melting the root node. Always cap expansion factor and candidate count. When nodes are added or removed, the routing table must be updated atomically. If the router and index store disagree, queries hit the wrong node and return empty results. The article warns about merge failures but doesn't show the atomic write pattern. Always write a new segment to a temp path, fsync, then atomically rename into the index directory. This prevents serving a half-written segment after a crash. The article mentions merge I/O can saturate disk bandwidth but doesn't quantify it. On HDDs, sequential merge I/O can push disk util to 100%, causing query latency to spike by 500 ms. Always separate merge and query disks or use I/O throttling. Use iostat x1 to monitor disk, await, if 20 ms, throttle merge rate. The article describes the root merge bottleneck but doesn't show the two-phase approach. First, each shard returns doc IDs and a cheap estimated score. The root filters to top candidates, then requests full features. This cuts merge time by orders of magnitude. The article notes that stale CTR features can underrank trending pages. Set TTLs on per document features and recompute at least every hour for high-traffic queries. Monitor feature age as a metric and alert if any feature exceeds its TTL to avoid serving stale rankings. To diagnose index corruption, first validate segment checksums. Monitor merge I/O with iostat x1 if await 20 ms, throttle merge rate. Run synthetic queries every minute to catch stale indices early. Let's run through some common interview questions. How does Google handle index corruption? Segment checksums, atomic merges, and replica validation. What is the role of the URL frontier? Prioritizes URLs based on freshness, importance, and politeness. How does multi-stage ranking work? First stage BM25 retrieves candidates, second stage DNN re-ranks. And a few frequently asked questions. What is an inverted index? A mapping from terms to document IDs for fast lookup. Why is crawl politeness important? To avoid overwhelming servers and getting blocked. How does Google achieve sub-200 ms latency? Through caching, parallel shard lookups, and early termination. Key takeaways: design feedback loops, not linear pipelines. Always validate segment checksums after merge. Monitor tail latency and shard QPS variance. And remember, model drift is silent, monitor feature distributions. Ready to go deeper? Up next, design Amazon, then design Netflix, then design Dropbox. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.